Earlier in this unit, we identified 4 different properties of waves that are exhibited by EMR. One of those properties was refraction. We defined refraction at the time as the bending of a wave when it went from one medium to the other. You saw yesterday that the reason that happens, the reason waves will bend when they go from one material to another is because they change speed. As a result of that speed either increasing or decreasing, the direction, the angle will either increase or decrease. In addition, the wavelength will either increase or decrease. That's called refraction. The change in direction due to a wave changing speed when it goes from one medium to another is called refraction. We saw yesterday this picture of this pencil that's in the water, and you've all seen this before in real life, right? When you have a pencil in water, it appears to be bent. And the reason that it appears to be bent is because the light that's reflecting off of the pencil is reflecting off, and then in one case, for part of this pencil, coming straight to our eyes. But for the other part of the pencil, it's bending before it comes to our eyes. So the light that's reflecting off of this spot is going straight to our eyes. The light that's reflecting off of this part is going straight, and then when it hits the boundary between the water and the air, it's bending. Our eyes get tricked. Our eyes think that the light has always traveled in a straight line. So if the light goes like this inside the water and then bends like this, then our eyes think the light always was traveling in this direction. So we're tricked into thinking the pencil is in a place other than where it really is due to the light bending, which happens because the light changes speed when it goes from the water to the air or from the air to the water. Okay, that's called refraction. We defined a term yesterday called index of refraction. We said it was basically the amount that a wave, or specifically in this context, the amount that light will bend, the amount that light will bend when it goes from one medium to the other. That was kind of the everyday understanding of index of refraction, just like when we defined momentum back in Unit 1, we called it how difficult it is to stop something, right? The everyday understanding. But the real scientific definition of momentum was the product of mass and velocity. Well, the real scientific definition of index of refraction is a ratio. The ratio of the speed of light in a vacuum, which is always going to be 3 times 10 to the 8 meters per second, divided by the speed of light in whatever medium that you're talking about. So for instance, light will travel at about 2 times 10 to the 8 meters per second through glass, and 3 times 10 to the 8 meters per second through a vacuum. So the index of refraction for glass would be about 3 times 10 to the 8 divided by the speed of light in the glass, which is 2 times 10 to the 8. So the index of refraction for glass would be about 1.5. But we also learned yesterday, it's not quite as simple as that. We learned that every material, let's say a glass prism, actually doesn't have one index of refraction like we see right here. If we say the index of refraction of glass is 1.5, well, it's not, it doesn't have that one value for index of refraction of 1.5. It actually varies slightly depending upon the color or frequency of EMR that you're using. Now, generally, for most purposes, we just say, look, we got one value for index of refraction. But strictly speaking, there is a value that's slightly smaller or slightly larger than that, depending upon the color that you're using. You guys have all seen this before, right? It's called dispersion. You probably haven't heard the word before, but you've all seen the rainbow being formed. And literally, it's a rainbow, right? Literally, it's a rainbow. That's how real rainbows in the sky are formed. You get light, white light, that's really just all the colors combined, red, orange, yellow, green, blue, indigo, and violet combined, and they hit something like a prism, or they hit something like water vapor in the atmosphere, and they refract, they bend. They change speed, and therefore they change direction. But red light changes speed, and therefore changes direction a different amount than orange and yellow and green and blue and indigo and violet change speed, and therefore direction. Therefore, the white light that was entering this new medium, glass prism or water vapor in the atmosphere, splits up. If each color bends a different amount, then it's going to come out the other side separated. That's dispersion. Now what you see in this diagram is that red light ends up refracting the least, or disperses the least. So we're going to say low frequency produces the least dispersion or the least refraction. And we'd say violet light, because it has the highest frequency, produces the highest amount of refraction or highest dispersion. Now, that means that for red light, it has the least dispersion, it has the least bending here, the least refraction. That means that red light or low frequency light also has the lowest index of refraction. Right? Remember we said the index of refraction is, in everyday language, the amount that light bends, the amount that light refracts when it goes from one medium to the other. If red light bends the least, if low frequency bends or refracts or disperses the least, then that must have the lowest index of refraction. You know what? I said that wrong. I said the red light must have the lowest index of refraction. Red light doesn't have an index of refraction. Glass has an index of refraction, right? It's not the color of light that has the index of refraction. It's the material that has the index. What I should have said is that glass or any other material has the lowest index of refraction for red light. It's not red light has the lowest index. It's glass that has the lowest index for red light or for low frequencies, or you could say for high wavelengths, right? So violet light, which is the highest frequency, the lowest wavelength, would disperse the most and or refract the most. Therefore, glass or plastic or water vapor for violet light must have the highest index of refraction. I want to show you a kind of a real life application of dispersion that everybody's seen before here. This is the Earth. We're going to draw the sun off in the distance. This is clearly not going to be the scale because I've got the sun drawn really small. It's way, way off, and to us it looks small, right? We know that the Earth is way heavier. It's like 1,000,000 times heavier than the Earth, so it's going to be really, really big, but it doesn't matter for this purpose. Okay, we've got white light, which I'm going to actually draw as black, ironically. A white light coming from the sun towards the Earth in every which direction. Okay, I'm going to draw one ray of white light, all the colors of the rainbow combined, coming from the sun. And then I'm going to draw the Earth's atmosphere here as just these little dots. Okay, that's the Earth's atmosphere, which of course varies depending upon where you are. It also varies depending upon the time of day, depends upon the position, depends upon the composition. Sometimes there's more dust in the atmosphere than there is at other times. Sometimes there's more water vapor, whatever. Okay. In this case, right now, at this moment, we've got white light coming from the sun. It encounters the Earth's atmosphere. Because it encounters at an angle, it's going to refract. It's going to bend, right? It's going from one medium, which is a vacuum in space, to another medium, which is the Earth's atmosphere. It's going to refract. But because it's white light and not just one color, the Earth's atmosphere will have a slightly different index of refraction for each different color, which means each different color is going to bend a different amount. Which one's going to bend the least? I'll tell you what, I never memorize this. You know what, honestly, you know how I answer a question like this? I think of that Pink Floyd album, Dark Side of the Moon. You guys know what I'm talking about? You see the cover of it? Like, picture, if you know what I'm talking about, like, picture it, right? When you picture it, you can picture the red light at the top and the violet light at the bottom. You can picture the light splitting up or dispersing like this. We'd have red light right here. We'd have orange light, green light, and so on, to violet light dispersing or bending the most. Make sense? All right. I'm going to ask you two questions. Two questions are, what time of day is it? What time of day is it right here? Guy standing right here on this part of the Earth, what time of day is it? Guy standing right here on this part of the Earth, what time of day is it? Right here, what time of day is it roughly? Yep. It could be morning, sun's rising, or it could be nighttime when the sun is setting. It could be either one, right? What time, and we know that because the sun is really low on the horizon, right? So whether it's rising in the east or it's setting in the west, could be either one of those. Okay, both of you guys are right. Okay, what time of day is it right here? Sorry? No. Where is the sun relative to you right now, Austin? Yeah, it's going to be like middle of the day, right? Because the sun is looks like it's pretty much directly above us, right? What color is the sky right here? What color of light do you see with your eyes right here in the middle of the day? Blue. The sky is blue, right? Really, it's not just blue. This is a bit of a simplification. It's a combination of blue and violet and some other colors, right? But I mean, it appears to be blue because certainly the light that you're seeing is toward that end of the spectrum. What time of day is it right here? Well, it's nighttime or it's morning. What color is the sky? Sometimes, depending upon the index of refraction of the atmosphere, in the evening or in the morning. Reddish, oranges, right? This is why. Okay, it's red in the morning or the evening because red light refracts less than blue light. It's blue in the middle of the day because blue light disperses or refracts more. The atmosphere has a lower index of refraction for red light, and it has a higher index of refraction for blue or violet light. It has a lower index of refraction for small frequencies and a higher index of refraction for big frequencies. That make sense? All right. So yesterday was a new equation as well. This is on one level kind of an ugly one because we got 4 different parts to it, 8 different variables. But it's really not that bad. It's called Snell's law. Just provides for us the relationship between angles. Okay, when light enters one medium and then comes out into the second medium, the angle that it goes in at, the angle that it comes out at. Theta 1 would be the index of the angle of incidence, the angle that it goes in at, as measured from the normal line, and theta 2 would be the angle that it comes out at. V1, V2, the speed in medium 1, the speed in medium 2, and so on. The trick here is you got to notice this one, right? I mentioned this yesterday in the podcast that you guys watched. Theta 1 over theta 2, V1 over V2, lambda 1 over lambda 2, and 2 over N1. Okay, we can all see that. We can all look at our data sheet and see that. But some of us just get in this habit of writing 1 over 2. And then even though it's on our data sheet, we still write this equation down wrong, and therefore we use it wrong. All right. You guys worked on some questions yesterday on page 668. Was there any issues with any of those 3 questions? Oh, all right. You also worked on worksheet number 17, questions 1 to 8. Let me put up some answers for worksheet number 17, questions 1 to 8. And then you can tell me if you had any issues with those. There's the first 4. All right, on that worksheet, we're going to take a look at question number 8, the last one that I assigned here. It says, determine the ratio of the speed of light in crown glass to the speed of light in quartz glass. First of all, the word ratio. The word ratio. We've seen that before, right? Ratio, compare. Okay, when we're comparing 2 things, we want to find a ratio. Remember, I don't remember what the question was back in our last unit, but we wanted to compare something to something else. And I used the analogy of comparing my age to your age. Okay, when I wanted to compare my age to your age, we really found a ratio of my age to your age, and we did that by dividing. So if we want to find a ratio of the speed of light in crown glass, we'll say the speed of light in crown glass to the speed of light in quartz glass, then let's divide. Let's divide the speed of light in crown glass to the speed of light in quartz glass. Only problem is I don't know what V is for either one of those. So that's an issue. Now, you could find V for each of them. You could say N is equal to C over V. So you could say, just hold off before you write this down though, because there is a shorter way to do this. You could say the index of refraction for crown glass is equal to C over the speed of light in crown glass. You could solve for this, solve for V, by doing this. Look back at your sheet to find the index of refraction for crown glass, divide C over N, and get that speed. Okay, I don't know what it works out to be, and I'm not going to find it because there is a shorter way of doing this. But you could do that. Okay? You could get the speed of light in crown glass. You could use the same equation to get the speed of light in quartz glass, except of course you're going to use the index of refraction for quartz glass. Okay, get those two numbers, divide the two, done. That's your ratio. That's your ratio. Now, what I did when I solved this, and I'm curious if any of you guys did this as well, what I did is said, look, I know what Snell's law says. Snell's law says sine theta 1 over sine theta 2 equals V1 over V2 equals lambda 1 over lambda 2 equals N2 over N1. If the ratio of V1 to V2 is a certain value, then the ratio of N2 to N1 is the same value. That make sense? That's two different parts of Snell's law, right? V1 over V2 equals N2 over N1. Just because I don't know what V1 and V2 are doesn't mean I don't know the ratio of V1 to V2. The ratio of V1 to V2 is the exact same thing as the ratio of N2 to N1, or NQ to NC in this case. What is the index of refraction for quartz glass? Anybody have that? Quartz glass was 1.47. And crown glass, I think I saw, was 1.52. When we do the math there, I think it worked out to be 0.947 or something. What was it? 0.967. 0.967. So, I mean, really, I haven't found a ratio. I've compared them, but I haven't found a ratio. The ratio would be 0.967 to 1, right? The speed of light in crown glass to quartz glass is 0.967 to 1. How many people got that number? Yeah. Which way did you do it here? Did you do it my way, like the shorter way, or did you find the speed? Shorter way? Okay, good. Both ways are good, right? But shorter way buys you a little bit more time for other questions if you're struggling to finish something.